We're continuing with Chapter 5, which is on the trig identities. In this video, we're going to start section 5.5, which this section is titled the double angle identities. But within this section, we're going to go through the double angle identities, but also the product to sum and sum to product identities. But we'll do these in the next video. Okay, so here's the trig identities sheet. We've now covered all of the fundamental identities, which include the quotient identities, the reciprocal identities, Pythagorean and even odd identities. We've gone through all of the sum and difference identities. We've talked about all of the cofunction identities. And now in this video, we're going to talk about the double angle identities. And then in the next video, we'll come to the product to sum and sum to product formulas. Okay, the double angle identities. When A is equal to B and the identities for the sum of two angles, the double angle identities result. Okay, so what they're talking about is with a double angle identity, it's going to be cosine or sine or tangent of 2 times an angle. And the way that they want you to think about this is from the perspective of the sum formulas. So for the sum identity for cosine, if A is equal to B, then you're left with cosine of 2A. And so if you plug B in, A in for B into the sum identity for cosine, you get, so okay, cosine of A plus A is 2A. And so you can write that as cosine of A plus A, and then expand it out with the sum identity, cosine of A times cosine of A minus sine A times sine A, and there you go. There's the double angle identity for cosine. Two other useful forms of this identity can be obtained by substituting cosine squared equals 1 minus sine squared, right? This is from the Pythagorean identity that relates sine and cosine, or sine squared is equal to 1 minus cosine squared. So, yeah, you replace with the Pythagorean identity relating sine and cosine, you can replace the cosine squared with 1 minus sine squared, or the sine squared with 1 minus cosine squared. And so they first replace the cosine squared with 1 minus sine squared and simplify and get another form of the double angle identity for cosine. And then they replace sine squared with 1 minus cosine squared, simplify, and get another form for the double angle of cosine. Okay, so there's 3 double angle identities for cosine. Double angle meaning it's cosine of 2 times an angle. All right. Now they then look at sine. So sine of A plus B, there's the sum formula for sine. But if A is equal to B, then they get sine of 2A is equal to, and substitute A in for B, and you get sine of 2A is equal to 2 sine A cosine A. And there's the double angle identity for sine. But there's only going to be one form here because there's nothing much more we can do with this. Okay, now take the sum identity for tangent, substitute A for B, expand out the formula, and you get the double angle identity for tangent. Okay, now it says, note in general for a trigonometric function f of 2A is not equal to 2 times f of A. Well, yeah. All right, so, and that's it. There's the double angle identities. They just come from taking the sum identities for sine, cosine, and tangent and setting B equal to A. And they're called double angle because it's the cosine, the sine, or the tangent of 2 times an angle. And so, but what about the double angle identities for secant, cosecant, and cotangent? Well, like we talked about with the sum formulas, there's no need to put those, tangent, okay, or cotangent of 2A is going to be what? 1 minus tangent squared of A over 2 tangent A, right? The reciprocal. And then cosecant would be the reciprocal of sine 2A, etc. Okay, finding function values of 2 theta given information about theta. So given that cosine theta is equal to 3/5 and sine theta is less than 0 or it's negative, find sine of 2 theta, cosine of 2 theta, and tangent of 2 theta. So there's multiple ways we can approach this, but we've worked similar problems like this in the previous sections. We can think about, we could use the Pythagorean identity relating sine and cosine to solve for sine theta. Why not start there? Okay. And, normally you couldn't do this, but since they give us the sign of sine theta, they tell us it's negative, then we can do this, because without that so cosine squared theta is 3/5 squared is 9 over 25. Okay, so sine squared theta, 25 over 25 minus 9 over 25 is 16 over 25. Take the square root of both sides. Sine theta is equal to plus or minus 4/5. Okay, but they tell us that sine is negative. Sine theta is negative, so we know that sine theta must be minus 4/5. All right, so we've got that. Now, to get sine of 2 theta, we need sine of theta and cosine theta. We have both of those. To get cosine of 2 theta, we need what? Cosine squared, or just cosine squared, or we could have cosine squared and sine squared. Well, we have cosine. We can just take the square of cosine. We could have actually found cosine of 2 theta without even doing this first step. Just plug the cosine theta in here. And tangent 2 theta, we just need tangent. Well, we can get that tangent from sine theta over cosine theta. So, all right. Finding function values of theta given information about 2 theta. So, okay, we just found trig function values given information about theta. Now they're going to give us information about 2 theta. So find the values of the 6 trig functions, standard trig functions of theta, given that cosine of 2 theta is equal to 4/5 and theta is in the second quadrant. All right, so we can get sine 2 theta and tangent 2 theta because we can say that we know that sine squared of 2 theta plus cosine squared of 2 theta is equal to 1. So sine squared of 2 theta plus 16 over 25 is equal to 1. All right, 25 over 25 minus 16 over 25 is 9 over 25. Okay, sine of 2 theta is equal to plus or minus 3/5. But sine of 2 theta is in the second quadrant. We know that sine is positive in the second quadrant, so this is going to be 3/5. Okay, now tangent of 2 theta is sine of 2 theta over cosine of 2 theta. So 3/5 times, and then cosine of 2 theta, they gave us cosine of 2 theta, that's 4/5. So okay. So now we've got sine 2 theta, cosine 2 theta, and tangent 2 theta. We can solve for tangent theta with this formula. We plug in tangent 2 theta and just solve for tangent theta. We can solve for, let's see, cosine theta with this formula. And then sine theta, we need, let's see. Yeah, we'll be able to solve for sine theta as well. Okay, well, actually, I couldn't choose that sine of 2 theta was, okay, I did this wrong. So if theta is between 90 and 180, so if you multiply that by 2, it's between 90 and 180. If I multiply this by 2, I would be in the fourth quadrant. If I multiply this by 2, I would be in the third quadrant. So theta, or 2 theta, is in the second or the third quadrant. Or 2 theta is in the third or the fourth quadrant. Sine is negative, so this is going to be negative, actually. So this would be negative. Okay, right, because this is sine of 2 theta. They gave us the theta. Theta is in the second quadrant. All right, but what they start off with is actually they take cosine 2 theta and they use the double angle identity and solve for theta or sine theta, but you get plus or minus square root of 1/10, and they choose the positive because theta is in the second quadrant. Okay, then they rationalize and there's sine theta, and then they could just go to just do the same process with the other double angle identities. Okay, verifying an identity. So verify that cotangent x times sine 2x is equal to 1 plus cosine 2x. Okay, so we'll work a bunch of examples verifying identities with double angle formulas. Simplifying expressions using double angle identities. So yeah, they're just going to expand. Well, okay, how would they do this? Oh, yeah, right. This is a double angle identity that combines, this turns into cosine of 14x, right? And then here you're going in reverse here. You're going back to the double angle formula. Same here, right? Sine 15 cosine 50 times cosine 15 is, if there was a 2 here, you could put 1/2 times 2, and you haven't changed the equation or the expression. Now 2 sine 15 cosine 15 is sine of 2 times 15 sine of 30. Identities involving larger multiples of the variable can be derived by repeated use of the double angle identities in other identities. Yeah, so you could do those identities multiple times. They could be compounded. You can think about. Okay, deriving a multiple angle identity, write sine 3x in terms of sine x. Sine 3x is sine 2x plus x. Use the sum formula for sine, and then you're going to get a double angle and a regular sine, or a double angle sine, a double angle cosine, and a regular cosine and a regular sine. Then expand out the double angles, and you're left with just a sine and cosine of x. And you can simplify that down to, it comes out to be 3 sine x minus 4 sine squared of x. And again, we're going to work a bunch of examples. So if I'm going through these a little fast for you, just check out the example problems. All right, determining wattage consumption. If a toaster is plugged into a common household outlet, the wattage consumed is not constant. Instead, it varies at a high frequency according to the model. W is equal to V squared over R, where V is the voltage and R is a constant that measures the resistance of the toaster in ohms. Yeah, so the voltage coming out of a wall outlet is not constant, right? It's AC voltage. That's what th're talking about. It's varying with time. Graph the voltage consumed by a toaster with R is equal to 15 and V is equal to, and there's the formula, right? 163 sine of 120 pi t. In the window in these ranges of the X and Y axis, how many oscillations are there? So they graph it going from minus 500 to 2,000 volts in 0 to 0.05 seconds. Okay, substituting the given values into the wattage equation gives, so, okay, there's the wattage equation to determine the range of W. We note that sine of 120 pi t has maximum value of 1. Yeah, so the expression for W has maximum, you take 163 squared divided by 15. The minimum value is 0 because it usually, the sinusoid goes from 1 to minus 1, but it's squared, so the minimum value is 0. Figure 8 shows that there are 6 oscillations. All right, so why did they give us this problem? I'm not sure, because we didn't use any double angle identity here. But yeah, that's definitely an interesting application of sinusoids is, like AC voltage. And, I guess they're pointing out that it doesn't matter inside the sinusoid, they got this big angular frequency, 120, all this stuff going on inside the argument of the sine or the cosine. Well, that doesn't affect the amplitude at all, right? What's going on inside the sine, it's always, no matter what you put inside of a sinusoid, the amplitude, it's going to oscillate between 1 and negative 1. In this case, it's oscillating between 1 and 0 because you're squaring it. Well, it's actually the amplitude it depends on what's on the outside. So it comes out to be 163 divided by 15. If you simplify all this, 163 squared divided by 15 is the amplitude. Well, or no, that's not the amplitude. That's the, I'm not saying that right. That's the That's the maximum value, and it's oscillating between zero and that maximum value, 163 squared divided by 15. So the amplitude would be 163 squared divided by 15, and all that divided by 2. Okay, in the next video, we're going to talk about the product to sum and sum to product identities.